CO2 emissions, the built environment this morning, and it was always a little bit from the aspect it's a burden. But I will try to show you that it's actually an opportunity. Now, coming from Switzerland, you know, we have this strange habit, we vote about everything. Everything in Switzerland starts with a vote. And last year we had this vote on this climate and innovation law. It was approved by almost 16% of the population, where we stated, okay, Switzerland wants to be net zero by 2050. This is a goal that we share with many countries. But then in this law there is also a sentence which says we need negative emission technologies. Now, I don't know how many of the 60% who voted yes read this word, negative emission technologies, and how many of them actually understood what it meant. But anyway, it's now in the law. And the question is why? Why do we talk about negative emission technologies? Let's do an artificial experiment. Let's assume tomorrow, by some magic, everybody on this earth stops to emit greenhouse gases. Zero, nothing, nada. What happens then with the CO2 concentration? It will decay over time, and of course also climate warming. And now you will say, okay, now they invited this strange guy from Switzerland and doesn't label the x-axis. This is what the x-axis looks like. And that's the problem. CO2 doesn't go away in a reasonable time. It's not like we had this problem of acid rain some 20, 30 years ago. We decided to take out the sulfur out of the heating oil, and within a couple of years, the problem was solved, because SO2 has a very short lifetime in the atmosphere. CO2 stays there for thousands of years. Oh, this is a problem. It's a fair question. If you are a little bit into climate science and so on, maybe you heard this expression of tipping points. Tipping points are irreversible changes in the climate system which could have quite severe consequences. One of them is the ice shield of Greenland, another one is the Gulf Stream, and there are a couple of others. And if we stay at plus 2-3 degrees or whatever for hundreds of years, for example, the ice shield of Greenland will disappear, and this is alone, Greenland alone is 7 meters of sea level. This is without what's going to happen in Antarctica. And there is a very nice website where you can play around. This is the city of Antwerpen, what it looks like now, and this is plus 7 meters. Oh, this is you need a new business model. And a lot of the largest cities on this planet are on the coast. So if you're, let's say you're invested into hotels in the first row in Miami, it's not a good idea. So, the other thing is, if the temperature increases by 1 degree Celsius, you have 7% more water in the atmosphere. And then things like what we have seen in Valencia a couple of weeks ago, this is the typical type of events we will see more and more. It's too much in a period which is far too short that we can handle. They got, I think, the rain of 1 year is in 24 hours. There is no infrastructure which can handle it. There's just no way. So, as a consequence, what we need to do is we have to decrease the CO2 concentration in the atmosphere actively. We cannot just rely on the natural processes. And this is where the negative emission technologies come into play. And actually, already, if you go for net zero, you can already see for net zero we already need a little bit of negative emission technology, because there are some which we cannot really bring to zero, like certain the ones from agriculture. But to be clear, I mean, still the first priority is to get to zero. But what we have to see, and this means just decarbonizing the energy system, it's really all about that. But we have to see that net zero, as difficult and as challenging as it is, it's only the beginning. In the second half of this century, we have to be massively negative. Something like 10 to 20 billion tons a year have to be removed from the atmosphere. So, we are living in a world which has been very much determined by cheap easily available fossil energy. And to be fair, I mean, for me personally, if I take the average energy consumption in Switzerland, I have 300 slaves working for me permanently. This is the equivalent of energy I use. And I must say, I have a comfortable life. I don't want to give them back, to be very honest. And this is the type of results we have. In Switzerland, the life expectancy at birth increased by about 40 years in the last 140 or 50 years. And this is due to this availability of cheap energy. It's very clear. We made an incredible progress as a society. It has been fueled by coal, by oil, and by gas. But that's the other part of the story, the increasing CO2 emissions. However, I think we are now in a transition phase, where we switch actually to renewable energy. And the good message is we don't have an energy problem on this planet. The sun is sending 10,000 times more energy than what we need. And people realize that. We work very close together with people in Oman. They just opened another tender for 4 gigawatt of PV. They have already 500 megawatts in operation. And the people in Oman say, look, we also want to supply the world with energy 30 years from now. It's not going to be fossil anymore, it's going to be renewable. And we have 3 things. We have plenty of sun, we have plenty of space, and we have quite a bit of money. And that's what we invest. And 2 years ago, they opened 2 test areas to install PV and produce hydrogen. The 2 test areas each were 36 square kilometers. This is what they call a test area. Huh? We have seen plans where they set aside literally thousands of square kilometers of land in the desert that they want to use. Whether this is all sustainable, I don't know, but it's just to say how they think. And of course the point is, production cost of electricity today is 1 to 2 cents per kilowatt hour. When they do it, it's basically for free. And then if you come from engineering, I mean 99% of this planet is hotter than 1000 degrees. There's plenty of energy. And we are and the other thing that just came out from the EAA, they expect now the global capacity growth for renewables by a factor of 2.7 from 2017 to 2030. You can see most of it is happening in China, but also the EU is almost doubling it. People are on the road because it's cheaper, it's available, you just have to do it. So this still might take 20 to 30 years before we are there, but I think this development is on the go and that's unstoppable. So once we have reached that, we get to this mining the atmosphere. We start to clean up the energy, the atmosphere using renewable energy. And the first step, of course, is carbon capture. And you have 3 sources. You can do it through direct air capture. You can take it from the oceans, because the oceans take up anything between 30 and 40% of the CO2 emissions. Or you use biomass, because this is what photosynthesis is doing, taking CO2 from the atmosphere and with the help of sunlight converted into hydrocarbons. It's not going to be cheap. Definitely not. And everybody is afraid of that. Who's going to pay for it? People from climate science say we probably have to remove about 600 gigatons. Might be 400, might be 800, but it's somewhere in that region. There is a Swiss company called Climeworks. They build those direct air capture facilities. This is their largest one that they went into operation this summer in Iceland, where they capture CO2 using cheap hydroelectricity and then pump the CO2 into the basaltic ground where it is converted into carbonates. They say at the moment, oh, where is this? It should be here. It's about 600 euros per ton. A lot of money. But we know cleanup is expensive. We had this wasteland field in Switzerland that had to be cleaned up because it was not tight towards the water. we paid 850 millions or 1,280 euros per ton for cleaning up this misery that we had there. Cleaning, even if you clean up your kitchen, you have to invest energy. You fight entropy in the end, and that's always costly. There's no way out. So, now let's assume, here I lost something. If it would ever stay at 600 euros per ton, there is no economy of scale, no nothing, and we would have to do that in, let's say, 170 years. We get to about, I think, 2.1 billions per year, a number I have no idea what it is. But the cost would be about 20 to 25% of the current yearly global energy costs. So the question is, can we afford that? Can we pay another 20 to 25% in order to clean up the atmosphere? If you think about the consequences, maybe we can. But another thing is, of course, how, if we could also generate added value, because what Climeworks is now doing, they filter the CO2 out of the atmosphere, pump it into the ground. So they do something good for the climate, but for the rest they only have cost, nothing else. And our idea is that we say, okay, this process of carbon capturing, we do it where we have plenty of renewable energy. So we capture the CO2. If you capture CO2, you always get much more water, which is always can be an added value. And then with additional sunlight and electricity, we produce hydrogen, renewable hydrogen. And then we convert the two into synthetic methane. Why do we go to methane? Well, there's a lot of talk about hydrogen society, but it's a typically chicken-egg problem. Are you going to build first a hydrogen network or hydrolyzers? Or you need someone who's going to use the hydrogen? Very difficult. Everybody's waiting for the other one. Methane is nothing else chemically than natural gas. So we have a global infrastructure to transport those molecules all over the place. We can start with a per mil of renewable methane, and we don't have to change anything in the logistics. We just add it. Nobody will realize anything. And then we bring that, for example, to Switzerland, and then we do a pyrolysis. So this is a thermal process excluding oxygen, and you get hydrogen again, but locally. And hydrogen you can use for high temperature applications in industry, you can run a gas power plant, whatever. But what you basically do is you import renewable energy from places on this planet which you cannot connect to with a power cable. Chemicals are much easier to distribute all over the planet, and they are also easier to store than electrons. And of course this is something which has a value. In Switzerland we have this discussion that once we shut down our nuclear power plants, we will miss about 8 terawatt hours of electricity in winter. And that's really, it's not an easy problem to solve. And now let's assume we would actually do it this route. Such an LNG tanker has about 1.5 terawatt hours. Let's assume that we lose 50% of the energy. Then we would need 20 tankers per year to fill this winter electricity gap that we have in Switzerland. So the 20 tankers, if I compare them to the 90 crude oil tankers that Switzerland is consuming, that's not a problem at all. We can handle that. And as I said, we have LNG tankers, we have a gas net, everything is there. We do not have to invest in infrastructure other than the pyrolysis. Good. Then the other thing is, how about materials? We still think about added value. There was a paper, because the second product you get from this process is coal, is carbon. So you convert CO2 into carbon, which makes it much easier to handle. CO2 is a gas, you have to compress it, and you have the two oxygen atoms that you have always with you, and you're not interested in the two oxygen atoms at all. They are not poisoning or anything. So here, we just only have the carbon, and it's a salt. We have the highest density of carbon. And there was a paper lately which stated that today we have more man-made material on this planet than dry biomass. So we were quite busy in producing materials as a human mankind. More material, man-made materials than dry biomass. And if you look at it, okay, 50% is concrete and 6% is asphalt. This is where the big chunk is. So how about trying to connect to those large streams of material? So what we do at the moment, we are working with biochar, so we go to the biomass route, but for the technical part this is not important. So we take this, we pelletize this with a little bit of cement, and then we use this as a lightweight aggregate for concrete. And the pellets actually have a net CO2 intensity of minus 1.05 kilograms per kilogram of pellets. Because this was something that the plants captured the CO2 from the atmosphere, and we just extracted now the carbon. And then we use that as an aggregate. You can see here also a tomography. Those aggregates stay constant. What you actually get is a concrete which is from the class C 30, 37. So this is really the concrete where you produce most out of it. I would not build a highway bridge with it. But for the rest, this is the type of mechanical strength you need in most things. And we have lately, in Dübendorf, we built those 3 buildings. And now I see why I use some of the numbers. There is something missing at the bottom. Anyway, we used 15,000 cubic meters of concrete. And I made a calculation, assuming we would have used this carbon concrete. What would have been the consequences? So typically, a standard concrete has about 200 kilograms of CO2 per cubic meter. By adding 200 kilograms of carbon pellets, we get basically to zero. We compensate all of the CO2 emissions related to the production of cement, concrete, and so on. And the total price for those 3 buildings would have been increased by 1.5%. Oh, come on, this is in the uncertainty of every construction project. Nobody cares. Of course, if you go to the concrete will be 50% more expensive. But for the whole project, it's neglected. Now, to be fair, we did not just only use concrete, it was actually reinforced concrete, so you have to include the steel as well, then you're at 300, so you would only get to 100. But we can do a couple of more things. If we do the pyrolysis of methane, we get a much denser carbon material than if we start with biomass. You could also use fly ash as a binder, etc. So it would be easy even to compensate for the steel. And once the steel production is not relying on fossil energy anymore, and there are developments in that direction, we will go to minus 100 to minus 200 kilograms of CO2 per cubic meter of concrete. And if you do carbon capture when you produce the cement, it's even better. So the result of that is, the more concrete, the better for the climate. This is the consequence. And it's not about Switzerland, we can forget about that. Here we talk about the billions of people on this planet who don't have a decent infrastructure yet. And they have all the rights to ask one and to get one. And infrastructures, concrete, all over the place. And does it matter in terms of climate? Well, let's do a calculation. Global demand for concrete is about 35 billion tons per year. If we are able to include 10% mass by mass of carbon, and we think we can get there, we would have 13 billion tons of CO2. And now, funny enough, there is an almost linear relationship between the CO2 content of the atmosphere and the temperature. It's about 0.45 degrees Celsius by 10 to the 12th tons of CO2. So this would mean within 170 years, if we would do that, we can turn down the temperature by 1 degree Celsius. So it really matters. Of course, we will not be able to do that with 100% of the concrete, I know that. But it's also not the only thing we can do. It's just to show you, this has a significant potential to do that, what I showed here, to reduce the temperature and to get away from a temperature range which might trigger those tipping points in the climate. And that's what we have to reach in the next 100 or 200 years. We also think about producing insulation materials, asphalt, many other things. I can show you. So, and then finally, you try to use those materials as long as possible, and then they have to go to a final sink. And the final sink is something very important. If you talk to someone from climate science, if you say, I want to be CO2 negative, you have to guarantee 1,000 years. And this we can do with the core. So, we have this mining the atmosphere, so we talk about CO2 capture, converted into base chemicals. Methanol can be used to produce polymers, keep them in the loop as long as possible, or maybe you also produce those things from biomass. Then you pyrolyze them, you use the carbon, maybe we can produce silicon carbide, we certainly have the hydrogen, we make lots of construction materials, we have to think about the final things, socioeconomic systems analysis is needed. So this is the whole menu that we work on. In the end, what we want to do is to create a vacuum cleaner for CO2. That's our vision that we have. And of course, nobody can do this alone. We have at the moment in the Institute maybe 40 people who are working on this project, but this is not even close to enough. I hope you're going to join us, because this is an effort that everybody has to work on. And this is our vision. We are developing materials and processes to enable the transition from a CO2 emitting to a CO2 binding society. And the built environment will be the main sink for the CO2. Thank you very much for your attention.